So what is linear algebra? So if we look at this word linear, it's got two parts. It's like line plus ear. Well, if we ignore the ear part, linear algebra just means we're going to be looking at things that look like lines. So if you think back to like an Algebra 1 class, you probably learned that lines usually have an equation that looks something like this, y equals mx plus b. That would be your classic slope-intercept form here, where m is your slope, your rise over run, b is the y-intercept. The other form that you might see this in, sometimes called like the standard form of an equation of a line, is if we move all our x and y stuff to the left, leave our constant terms on the right, you might end up with something like ax plus by equals c. And so this right here, this is the key form for the types of equations that we study in linear algebra. So this right here, this is a key example of a thing that's linear. And what really makes it linear is that you just have constants times the variables, and then these things are added together. So that's what linear is. What about things that are not linear? So it turns out we cannot have something with an x squared. This makes it not linear. You also can't have an x and a y multiplied together. That's going to make it not linear. Also more complicated functions, things like a square root of x or a 1 over x or something really crazy like an e to the x. All of these things are not linear. So there's a more sophisticated reason why this is the case. Linear ultimately has some property about distributing over a sum of inputs, which all these would fail. But for now, you can also think about this as if you graph some of these, you're not going to get the graph of a line. Things like this, you will get the graph of a line. So at the start of a linear algebra course, the focus is on studying these linear equations and more specifically, systems of linear equations. So a system would be whenever you have two of these things, two linear equations, and what you're trying to do is find a solution to that system. So we could have this as something like an a1x plus b1y equals c1, and then we've got another one of these with twos. a2x plus b2y equals c2. And we're considering this as a system, so we have two linear equations that each represent a line, and we're trying to find the solutions. So a solution to a system, this is an ordered pair xy in this case, since we have two variables. This is an ordered pair that satisfies both equations simultaneously. Okay, so let's look at an example here. All right, so here we have a system of two equations. So our first equation is 2x plus y equals 3. Our second equation is negative x plus y equals 0. So first, let's draw a sketch of each of these lines, as that'll help us get an understanding of the solutions here. So if we call this one L1 and we want to graph it on our little basic coordinate system here, well, one thing we could do, we could put this back into slope-intercept form. We see we have a y-intercept of 3 and a slope of negative 2. Y-intercept of 3 would put us right here. A slope of negative 2 means we would go down 2, right 1 to this point here, and our L1 line looks something like this. And what about our L2 line? So this L2 line, if we do something similar here and rearrange it, we can see that this is the line y equals x. So that's just our slope 1, y-intercept 0 here. And it goes right 1, up 1, so it'll also go through this point right here. And so this is what our L2 looks like. And so if we're trying to find solutions to this, we actually already have the answer right in front of us. So a solution, this is an xy pair satisfying both equations. So using the graph, what we can say is, well, if the ordered pair satisfies the first equation, that means it's a point on this line. So if that same ordered pair also satisfies the second equation, it's a point on the red line. So if a point is simultaneously on the blue line and the red line, well, then it must be an intersection point. So that's the key way to think about this geometrically, that a solution is an intersection point. So if we look here, it looks like we have a solution from this intersection here, which would just be 1, comma 1. So this is sort of our guess at a solution based on the picture. Let's verify that algebraically. So that is, when we plug in this x and y coordinate, x is 1 and y is 1, it better make both of these equations true. So let's do that check real quick. So we would do 2 times 1 plus 1, and that should equal 3. So let's see. So we do 2 times 1, that's 2, plus 1, that is 3. So that one checks out. Let's try the second one. So you have negative x plus y equals 0. So plug in x is 1, so that's negative 1 plus positive 1. Well, what's that? If you add those, you get 0, just like it's supposed to be. Hooray! So this verifies indeed that 1, 1 is a solution. Okay. But there can be some more complicated things that happen. What if we instead had two parallel lines? Well, then those never intersect. So that's another possibility, is that there's actually no solutions if they don't intersect. So let's see what that might be. All right, so we've got another system here, 3x plus y equals 2, and 3x plus y equals 0. So this is already a little suspicious. These two sides look the same, but the right-hand number is different on each one. So if you think this through and try to guess some answers or something like that, you would see that you're gonna end up with a problem. Because whatever you pick for x and y, when you plug that in the left-hand side here to 3x plus y, well, there's no way it's going to be equal to both 2 and 0 at the same time, unless 2 and 0 are the same, which they're not. So we should be able to see how this here is an example where we have no solution. So if we graph each of these again, just to visualize this, our L1 line would be y equals negative 3x plus 2. So we would have a plus 2 y-intercept here. Let me finish putting together these little axes. So we start at 2, then we have a negative 3 slope. So we go down 1, 2, 3, and right 1. So we would have a line that looks like this. For our other one, for our L2, if we do the same thing, we would have y is just negative 3x plus 0, right? So we would have a 0 intersection here, and then we do something similar. We go down 1, 2, 3, and right 1. And so, if you graph this, a little more precisely, you could see that indeed these two lines are parallel. So when they're parallel, there are no intersection points. We know our intersection points, those just correspond to solutions to these equations. So that means in this case, there would be no solutions. Okay, and for one last thing, there is a third case that can happen. So we could have, in the last one, we had one exact solution to this system. In the second case, we had no solutions, where you would never find any ordered pair that satisfies both equations simultaneously, right, which we can see with our parallel lines. The third case is there can actually sometimes be infinitely many solutions. So if we change this slightly, we could see an example that looks like that. So if we do a 3x plus y equals 2, and then here what I'm going to do is I'm just going to take this equation and I'm going to double everything. So we've got 6x plus 2y equals 4. So in this case, what will happen, if we graph each of these, well, if we convert this into our slope-intercept form, we know this one is y is negative 3x plus 2. If we do the same with our L2 here, Well, we could start by solving for 2y by subtracting 6x. And then when we divide by 2, we'll see we get actually the exact same equation 2 times. So if you were going to graph something like that, the blue and the red line would just look like exactly the same, right? We'd have the blue one going here to here, and then the red one would sit like exactly on top of it. So we could do something like draw as a dot. And so in this case, we really have 2 copies of the same line. And so what this means is any point on the line, we can say the, because there's only one of them now. Any point on the line is a solution. So this is when we have infinitely many solutions. Yeah, so any ordered pair you can name on this line, that's a solution. So you should be able to go in and check if you put in like 0, 2, that's the solution, should satisfy both. Or if you put in what we got here, like a 1, -1, that should also be a solution, and so on, any point you find here. Okay, so those are the three cases for the solutions to a system of 2 equations and 2 unknowns.